In today's session, we'll be discussing about pressure measurement instruments. So first of all, three different types of pressures, like atmospheric pressure, which is surrounding to us, then absolute pressure, uh, and gauge pressure. You are quite familiar with these terms because you already learned this in fluid mechanics course. So whatever the pressure which we are measuring using measurement instruments, they are with reference to the atmospheric temperature, and which is with reference to the atmospheric pressure, and that's why that measured pressure by instrument is called as a gauge pressure. So if you want an absolute value of or absolute pressure, then it's a like atmospheric pressure plus gauge pressure, right? But if like a negative pressure, like in case of vacuum, then absolute pressure is the subtraction between the atmospheric pressure and the measured gauge pressure. Now these are the different pressure measurement units. Again, you are quite familiar with this. I would to introduce this one tar, which is 1 mm of Hg, which is generally used to indicate the vacuum pressure. So in this topic or in pressure measurement chapter, we'll discuss two instruments for vacuum pressure measurement. One is Pirani gauge, and second is McLeod gauge. So at that time, we'll be using this tar as an indication of pressure. Now, basic classification of pressure measurement instruments. So very high pressure, which is more than 1000 atmosphere. So bourdon pressure gauge, diaphragm pressure gauge, electric resistance pressure gauge, right? So this we are generally using. Similarly, medium to high pressure range, it is 1 mm of Hg to 1000 atmosphere. So for that, again, bourdon tube and diaphragm gauges are used. For low pressure measurement, you are familiar with the manometers, right? So manometers, they are used for low pressure measurement up to 1 mm of Hg. And vacuum pressure measurement, we are using McLeod gauge, thermal conductivity gauge, and ionization gauge. So Pirani gauge, that is working on thermal conductivity principle. So we'll be discussing McLeod gauge and Pirani gauge, which are used for vacuum pressure measurement. First of all, very basic arrangement, which is called as a ring balance manometer, which is also called as a mechanical displacement type instrument for pressure measurement. Here we have one circular glass tube in which kerosene or paraffin is filled, right? So and this here you can see this glass arm, right? And this center of circular tube, that is connected to one hinge, right? And right is written as a nifage. So one hinge is by hinge one the center is connected. Then here you can see we are having one mass which work as a pointer here, right? So if pressure is not applied, because if you look this circular tube, that is having partition here at this position, otherwise this entire tube is connected, but it is sealed at this portion, and we have two openings. One can be open to atmosphere, which is called as a low pressure side, and high pressure side, that is connected to your application where you want to measure pressure, right? So suppose both the ends are open, then you can say pressures are balanced on both the sides. Both the sides you are having atmospheric pressure. So at that time, this mass which is attached to this tube, that will remain vertical here, that will remain vertical, right? Now what happen is, if you give some pressure source to this P1 end, right, then due to the pressure difference, because some that fluid pressure that is applied to this liquid over this liquid, right? So some force is created on this side. Now atmospheric pressure is applied on this end, so there will be a pressure difference, and that pressure difference that will create unbalanced force. And because of that unbalanced force, when that unbalanced force is more than the horizontal component of this mass, then this tube, this glass tube, will rotate until again it get the equilibrium state, right? So one pointer is connected here. So because of rotation of this glass tube, that pointer that will move on the scale, and the scale is already calibrated in terms of pressure. So if you look the pressure measurement range, then that is 300 mm of water, and maximum tilt 30 degrees allowed, because after that that the scale becomes more non-linear. That's why it is restricted up to 30-degree tilt. Now if you look here how this equation is formed, then this P1 and P2, as I told you, differential pressure is applied on this glass tube, right? Because of that we'll be having some force here. So that differential pressure into this small a is the area of this glass tube, right? So it's a pi by 4 small d square. Suppose small d is the diameter of this glass tube, right? So that is the a, and this r1 is the mean radius of this glass tube from the center. So this is r1, right? So this P1 minus P2 differential pressure into A, that is the unbalanced force, and that unbalanced force that is creating some torque by multiplying it with R1, right? And that torque is balanced by the horizontal component of this mass, because this M into G, that is the downward force. Now as because of the differential pressure, if this M is moved up, then again if you look, this M is applicable along this line. Now if you resolve it, and if you find out component which is opposite to this pressure difference force, then that is W sine theta, right? And W sine theta into R is again this distance. So R is the distance of this mass from the center of tube, right? So in this way these two forces are balanced. One is the gravitational force because of this mass M, and second is due to the pressure difference, the force acting on this liquid. So this is the simple ring balance manometer which is used for low pressure measurement. And to so is there any query now in this explanation?
सर फ्लूइड स्लाइड नहीं हो जाएगा मतलब तो हाउ विल इट रोटेट सर रोटेशन कैसे होगा आई एम नॉट एबल टू अंडरस्टैंड हाउ विल द पॉइंटर रोटेट बिकॉज़ आई थिंक द फ्लूइड विल मतलब फ्लूइड इज नॉट स्टिकिंग टू द सरफेस सो इट विल नॉट स्लाइड हो जाएगा ना सर इट विल
Am I audible?
हेलो
Check. Okay, if you have any query, then you can write in chat. There might be some problem with the speaker at my end. Yes, mass is attached to ring. Okay, so shall I move further then? Okay, so to understand this, let us solve one simple problem. So calculate the maximum differential pressure measured by ring balance manometer with following data. So this is what you are defining specification of the ring balance manometer. So this much of weight is suspended, then average radius of ring means your R1, that is 210 mm. Tube diameter small d is 90 mm. So based on that you can measure, you can calculate small a. This is to be used in this equation, small a, right? Distance of weight from the center means it is this distance, this R2 distance. So that R2 distance is 300 mm, and maximum deflection of ring is 30 mm. So this theta which you allow as per the specification, it is given up to 30 degree. So if you solve, then you can find out a maximum this much of pressure difference you can measure using this arrangement. Now if you look here, if I want to change the pressure measurement range, I need to change the weight which is to be attached to this ring, right? By doing that, you can change the working range of the instrument. Okay, so for a particular weight on this ring, you are having pressure measurement range. Now next is about bourdon tube pressure gauge. So as in laboratory we have already discussed about bourdon tube pressure gauge. This is the simple mechanism of a bourdon tube pressure gauge, where you have one elliptical shaped tube, right? So this end of tube is closed, this end is free, and that is connected to one pipe, and this pipe is connected to your pressure source, whose pressure you want to measure, right? Now this closed end, which is free end, is connected to sector through mechanical linkages, and this mechanical linkage length that will actually define the magnification, right? So this length as well as this distance, this sector distance from the hinge point, right? So these two, they will define the magnification. Now what happen is, as we give pressurized fluid to bourdon tube pressure gauge, then this elliptical tube will try to change its shape from elliptical to circular, and as this end is fixed, this end is free, so this end will try to deflect, and deflection of this free end, they are transmitted to sector through mechanical linkages, and sector is connected to pointer, so pointer will rotate, this pinion, and this pinion will rotate, and because of rotation of pinion, that this pointer that will move on the calibrated scale, right? So basic principle is again here that is shown. It is based on the deflection of curved beam. So basic theory is given for means you might learn in the design courses about deflection of curved beam. So here you can see this this delta P that will cause delta A deflection, right? And this diagram is giving you idea about the different dimensions. Major axis is of X, and minor axis of this elliptical tube, that is Y, and this is called as a bourdon tube. That's why this gauge is called as a bourdon tube pressure gauge. So this is the equation which correlates delta P with the pressure difference P, right? So this is derived based on the curved beam deflection theory. So we are not going in much detail about derivation of this equation. I am just giving you idea that this is the relation, how this delta A is related with the P for the calibration of this bourdon tube pressure gauge, right? Where T is the thickness of tube, A is the Young modulus of tube material, right? Here this small a is the length of this bourdon tube, right? So these are the different meaning of different terms which are indicated in this equation. So these are the different materials which are used as a tube material, and based on that pressure range is defined. Like phosphorus bronze, if you are using as a tube material, then you can measure up to 7,000 kilonewton per meter square. Alloy steel or monel, that is used for higher pressure range up to 63 or we can say 630 megapascal pressure measurement. Now sources of error and their remedies. So this plot is giving us idea about true value to the measured value, which you have done in the as a part of the calibration in the laboratory, right? So three major sources of error. First, or three types of errors in bourdon tube pressure gauge. First is zero error. So what is zero error? For any non-zero value, pressure value, instrument is giving you some positive value, right? So your true value on x-axis we have true value, on y-axis we have measured value. So there is no pressure given to the this bourdon tube pressure gauge, but still that pointer is showing us some positive value, and this value remain constant throughout the range of measurement. That's why it is called as a zero error or constant error, right? So to see the internal mechanism, let us go to this video.
Welcome back to the Kodiak classroom. In this lesson, we're going to learn how to utilize an adjustable pointer. Now, looking at this gauge, you can see that it's reading roughly around 7 to 8 psi.
The video is not visible.
You are not shared.
Welcome back to the Kodiak classroom. In this lesson, we're going to learn how to utilize an adjustable pointer. Now, looking at this gauge, you can see that it's reading roughly around 7 to 8 psi. The problem is that there's 0 psi in the line. So obviously, this gauge is off of 0. So let's fix that. It's an easy, quick fix out in the field as long as you have an adjustable pointer. The first thing you need to do is obviously identify if your gauge does have an adjustable pointer. And how you do that is you take a look at the pointer itself. If there's a flat head right up towards the base or in the middle, it's going to be an adjustable pointer. So we can do this. Now, as long as your gauge is roughly off by between 1 to 10% of the nominal range, so within the 100 psi, this is obviously around 8, you should be able to adjust it. If your pointer is pointed at 40 at 0, it needs to be fixed another way. The adjustable pointer is utilized just to kind of fix roughly around 5 to 10% when it's off a little bit. So what we're going to do is we need to get access to the inside of the gauge in order to move this pointer. So most or all, actually, adjustable pointer gauges are going to have a bezel to remove. This is a process gauge, so it has a bezel on the inside with notches here, so we need to remove that. You take a flathead screwdriver and a hammer to knock it down here, and we're going to loosen it counterclockwise, get it started, lightly tapping it. You can remove the rest by hand just by loosening it out. Okay, so now the bezel came out, and that's what you have. So now we need to remove the lens. You can take a small flathead to get it started. You're going to see either glass or plastic. In the case of glass, you want to be really, really gentle because pushing it too hard, you could crack the lens, and we don't obviously want to do that. So we're going to get it started here to kind of get it out. Okay, so we got that out here. And you may see a black elastomer and O-ring on the inside. That's utilized to keep dust from getting in, and if you have a gauge that's liquid filled, which this one is not, it'll help keep the fluid from staying in as well. We can ignore that in this case since it's dry. We don't need to touch that. We have access to the inside of the gauge anyways, and we can get moving. So what you do is you take your forefinger and thumb, put it at the base of the gauge, take your flathead, put it up against the screw, and then you're going to turn it clockwise to move it, the pointer clockwise, counterclockwise to move it counterclockwise. So it's pretty basic here. So we're going to move it a little bit here. You don't need to turn it that much. As you see, the pointer just went back down a little bit. So we're going to get it right within that 0 box. I'm going to turn it a little bit more. And there we are. So now this gauge is reading that 0. So let's go backwards. We're going to put the left screwdriver in your hand. If there's any vibration, it'll stay in. You shouldn't be able to move it with your hand very easily. And that's it. This gauge is ready to go.
Okay, so what we are doing here, if you look in this schematic diagram, we are having one spring, right? So when pressure is removed, then what this spring will do, the spring will again bring this pointer back to the 0 value. But suppose because of the change in the clearance, or because of the backlash between this pinion and sector. Now suppose for 0 pressure, this pointer is showing you some value. Then if you look in that video, what they have done, they have tightened this coil spring. So by doing this, you are changing the stiffness of spring, and again you are bringing back this pointer to the 0 value. Right? So this is what they have done in the removing that 0 error, which is present in the bourdon tube pressure gauge. Then next is multiplication error. So if you look what it is, right, in case of multiplication error, that error is not remaining constant. Error is not remaining constant, but its ratio remains constant. I mean, the slope remains constant. So it is having it is following this line, right? So calibration value itself change. That is what called as a multiplication error, right? So gauge tends to give higher or lower reading. So wrong setting of multiplication mechanism. So this mechanism is called as a multiplication mechanism. This mechanical linkages, right? So how to rectify this error? Move connecting link inwards. If gauge reads low value, means if lesser value is indicated, then move this link towards inward, towards this free end, right? And if it is showing high value, then move connecting link outward, right? So by doing this, you can again try to remove this this multiplication error. And next is angularity error. So angularity error is the completely hysteresis error, right? Which is non-linear. So it is indicated here. This angularity error, that is non-linear error. So it is difficult to remove non-linear error completely from the system, right? So these are the 3 different types of error in bourdon pressure gauge. Now the advantages and limitations. So low cost, measures gauge absolute and differential pressure, simple calibration with dead weight calibration tester. So this is what we have used in our laboratory, available in several range by changing the tube material, easily adapted to strain, capacitance, magnetic and other electric transducers. So this is how we are getting digital pressure measurement instruments nowadays. Now limitations, hysteresis error is present because it is working on gear mechanism, slow response, that is because of the inertia of structure, required geared movement for amplification because it is entirely a mechanical instrument, right? So these are the limitations of bourdon tube pressure gauge. Next is diaphragm gauge. So if you look what change is made here, these are the two ends which are to be connected. Suppose if you want gauge pressure, then one end is connected to your pressure source and second end is kept open in the atmosphere. Now when pressurized fluid applied on a diaphragm is nothing but like a disc, right, thin disc. So because of that pressure, this disc will deform, and deformation of this disc that is transmitted to this pointer. So because of deformation of this pointer that will deflect and that will indicate the pressure. And this is the relation of diaphragm deflection with the pressure change. Right? So this is internal mechanism. It is look like this. This is the diaphragm, right? So when you give pressure to the diaphragm deflect, and the deflection of diaphragm that propagate to or that transmitted to this pointer through mechanisms which we are using in bourdon tube pressure gauge. These are the diaphragm gauges, how they look like. So here diaphragm is fixed between two plates. This is the diaphragm. Now this is the basic information, like metallic diaphragms. So their material is mentioned here for different pressure limit application. So as we have already discussed, it is for low pressure to high pressure measurement. Non-metallic diaphragm, then we are using these materials as a diaphragm material, and then pressure measurement range is given. Now this example is based on the this equation which is shown here. Based on this equation, this example is given. It's a simple example based on this given data. If you feed it, that will give you the thickness of diaphragm which is required for pressure measurement up to 2.5 megapascal. Next is Bellow pressure gauge. So here only change is deformation member is changed. In the first case we are having bourdon tube. In second case we are having diaphragm. Now this time we are having bellow, right? So bellow is like a spring element, right? It is look like this. So when you give pressurized fluid, then this bellow that will compress, and that compression that is transferred to this pointer, and pointer that will give the pressure through this type of sector and pinion arrangement. So internal arrangement is again same. It is similar to the bourdon pressure gauge and diaphragm pressure gauge. Only change in the deflecting member. Now here we are having diaphragm, right? So it can this bellow pressure gauges, they are having more sensitivity compared to the diaphragm and bourdon tube pressure gauge. These are the different materials which are used for manufacturing of bellow.